said, I'm Mariano. I'm the head of engineering of C-Labs. And I'm going to be talking today about how you can scale rollups using EigenDA. So first things first, I guess something about me. I'm from Argentina. I'm not really part of Eigen or EigenDA, so I'm not going to be speaking here from okay, it's my company, I'm going to try to shield it. Actually, I'm more of a customer. I'm part of celo. Celo, it's a L1 chain. It's a chain that it's basically in its own journey to become an L2. It's basically an EVM chain. That I guess one of the most interesting properties to me is that we kind of modify, we introduce new types of transactions, so you can actually pay gas using ERC20s. So for example, you can use unpaid gas using Tether, USDC, or celo Mentos families of stablecoins, which is like CUSD, Euro, or even local currencies in different countries. As I said, one big thing that basically is relevant for celo today is we are in our journey to become an layer 2. We started talking this around a year ago. It's been quite a journey because we wanted to basically assess all the different technology that was available and see what was the best stack options for us. And that's why I think I can really go and speak about you, different options, different trades, and how you make that decision. No? Just recently, we introduced our first testnet for the L2. It's called Dango. Something interesting is I guess, it's not that easy to, it's not like we are launching a new chain, we are migrating an existing chain. So imagine from the user perspective, the user won't really notice. It's one day they be connecting to nodes that are running an L1, and next day it will be an L2, and for them it will be exactly the same. So same state, same everything. And so doing that particular migration is actually particularly tricky, and that's part of what we need to do, and Dango is our first experiment of doing that. Actually, later this year, later on September, we'll be migrating actually our first testnet that it's live. That's a testnet that has many years of history, and we expect, I have some people here that probably are not going to agree too much with me, but we expect that maybe sometime next end of the year, we'll be able to get to mainnet. Okay, so that's enough about celo. Let me talk about Eigen. In particular, I'm going to be talking about Eigen and OP. So you know Optimism. Optimism has its own stack. It's called OP stack. And that's actually what we're using. We're using OP stack. And we're using EigenDA, and I'm going to try to talk to you about how you can use those two and how they work together. So first things, what is EigenDA? So first thing is you need to understand what is Eigen. No, I know how many of you know EigenLayer, but EigenLayer, it's a risk-taking solution. So the idea here is that you can use the staked ETH for Ethereum proof of stake to run other services. Now you know that most of these services have this idea of economic security, that some nodes are doing some job, and if they fail or do something bad, they get slashed. No? And so the idea is by reusing the stake, by reusing all that ETH that it's staked for Ethereum, they can start running other services, and they can get slashed for running those services in a bad way. No? One of those services is EigenDA. So EigenDA is, I guess, they call this service AVS, and EigenDA, it's actually also Eigen solution for data availability. No? And why do we care? No? Why do we care about data availability? I know how many of you work on infrastructure, or you've seen that we have rollups. Rollups used to be, I guess, cheaper, but not as cheap as they could. And one of the main blockers was the data, like the data requirements. A rollup basically takes execution outside of Ethereum, but the data still goes to Ethereum. And that's why Ethereum was becoming this huge bottleneck. Ethereum has its own plans to solve this problem. No? So you've heard about product sharding, which is already live, and you probably heard about dank sharding, which is something that's going to come later. And the whole idea is Ethereum is becoming this kind of huge settlement layer or data availability layer where all these rollups or layer 2s are going to send their data. Now, that's maybe an interesting future, but we don't know when or how it's going to arrive, or if it will arrive and it will actually be able to cope with all the demand for space. So having off-chain data availability solutions is actually an interesting idea, and for that you can mention Celestia, for example, that you probably also know, and Eigen would be another one. Now, I'm going to do a step back and try to explain, so we have a common framework, how does a rollup work? So, how does it work? No? So, we have Ethereum. No? You have like blocks on Ethereum. You have the sequencer. You have a sequencer. You have a validator. These are like rollup roles, no, that are like basically have a job within running a rollup. No? And you have the layer 2. These are like the blocks of the layer 2. So what's going to happen is like you're going to have this person, the sequencer, that is going to start creating blocks. No? It's going to go define, okay, I'm going to get these transactions, I'm going to put them into a block, and I'm going to say, okay, this is a new block. No? Now, it's not only going to do that, it's going to get the data for those transactions and it's going to send those to Ethereum. No? That thing called their TX data. Why do you need to do that? The whole idea is like, I guess, with chains in general, you know that whenever you are, I don't know, any node of a chain and you want to sync and you want to learn what's the canonical chain, you need to go and get all the blocks. And how do you know it's canonical? In proof of stake, because it's signed. In a rollup, it's because it's there. No? And it's there, signed by the sequencer, and has some kind of maybe other authentication properties. So full nodes will go and basically read the TX data from there, and that's how they will be able to sync to your rollup. Now there's, I said that it's only sending the TX data. So again, if you go back to analyze an Ethereum block, what you'll find, an Ethereum block has the transactions, and it also has what they call like the state root. The state root is the result of applying all those transactions. And so in a rollup, basically that has been divided into two jobs. No? One job is to get the transactions out there. Okay, these are the transactions that we need to execute in this order. So that's one job, that's the sequencer job. And then there's another, which is the validator, that's going to say, okay, and this is the result of executing those transactions. Now, you could argue that this is not entirely needed all the time. I guess if you're running your own node and you know the transactions that you need to execute, you can execute them yourself and you get the result. No? But this is actually become quite important if you want the layer 2 to communicate with the layer 1, in this case Ethereum, because the validator is going to compute that state root, it's going to send it to Ethereum, and then Ethereum is going to, I guess Ethereum smart contracts are going to be able to say, oh, because the state root, the result of the layer 2 is this, I can do this other thing on the layer 1. That's basically bridging, you know? Or what they call in this lingo, it's like a validating bridge, because it's in the term of bridges, basically, we are validating the whole state transition. Now, how does this change when you go and try to do off-chain DA? So when you try to do off-chain DA, well, you need to introduce another actor here, which is the DA provider. And so now this thing that I would say that you have like 3 jobs is now divided in 3 jobs. So the sequencer is going to be responsible to sending the data commitment, but it's going to send the data to the DA provider. What does that mean? It means that basically, guys, basically, the Ethereum is going to still be responsible of giving you the order in which you need to process all this data. No? Imagine this is not like just one time. You are doing this for every block or for every batch of blocks. And so Ethereum is what they call like consensus layer, because it's basically giving you the order of all the pointers to data. But then you need to go get a pointer to the data and ask the DA provider to, okay, what's the data that I need to process? Okay. So.
Is Celestia off-chain?
Sorry?
Is Celestia DA off-chain? That's what you mean by off-chain?
Celestia is also off-chain, yeah. I'm here talking more of a general like off-chain DA. I'm going to be talking about Eigen DA, but Celestia will be the same. So this general process will be the same every time you see an off-chain DA. No? You are going to send the data elsewhere, but then you're going to get like a commitment of that data from the DA provider, and you're going to send that commitment to Ethereum. You can imagine that that commitment is like a pointer to the data. Okay. Before getting into EigenDA, another thing I want to mention from the OP stack is what they call OP Plasma, or I guess they used to call OP Plasma. They are now calling like OP AltDA. And the idea is that this is a protocol for off-chain optimistic DA. What do I mean by this? No? So I guess this is more or less the same that I just showed. No? The sequencer at some point is going to go and post a blob, so this transaction data, to the DA provider. In this case, it's going to be called like the Plasma server. And the full node, when it wants to sync, when it wants to basically get all the transactions, it's going to go to the same Plasma server and going to say, hey, give me the blob for that key. No? And by key, I say it's like this DA commitment I was talking before. No? So the sequencer posts a blob to the DA provider, the Plasma server. No? This is something like this. And it's actually an HTTP protocol, so the idea is like you're going to basically do like a post, and you're going to send, okay, this is the blob, and as a response, you're going to get like this kind of X encoded commitment, so you're going to basically get, okay, this is the commitment of the blob. You can use this commitment to later go fetch it, which is what the full node will do. No? So it's very basic. It's not really telling much. What is the optimistic or what's the interesting part here? It's what they call like challenges. No? So there's an attack that you can do through these systems. Now imagine, we know that, I know, it's very hard to attack Ethereum. It has like a ton of economic security. So it would be impossible to, okay, it's quite hard to go and change those DA commitments, to do like a reorg, or to do like a reorg, like a double, what people call like double spend attack, but in this case it's just trying to change the history of Ethereum. But what if the DA provider at some point decides not to serve the data? No? So you have a DA commitment and say, hey, give me the blob for this commitment, and the DA server says, okay, to you I'm not giving that, or to you yes, or I don't give that to anyone. No? What happens then? And that's actually what they call like a data withholding attack. No? And actually in optimistic rollups, that could be quite serious, because you know that optimistic rollups have these, okay, so I haven't explained that, but basically when you send the state commitment, there's a challenge period of 7 days in which anyone or some parties can go and say, okay, that state root that you said, it's actually incorrect. Now, what happens if the DA provider decides to withhold data for 7 days? So no one is actually able to get the data, execute it, and challenge the results. And so that way would be basically a way to generate a hard fork or do a double spend attack on the layer 2. So what OP people thought was, okay, we're going to create something that's called a challenge. No? And the idea is like, when you are syncing, when you are a full node, you start getting and you start querying the DA provider the Plasma server. And if the Plasma server is not giving you the data, you're going to send a challenge to a smart contract on Ethereum. And you're going to say, hey, I can't get the data, so put it here. Put it on the L1. No? Again, the whole idea is like, I'm going to be paying for the cost of that as a node. So you can do this kind of this Griffin task. But what will that generate is like the DA server will need to either post the data there, or it could choose not to. But if it chooses not to, the L2 itself will reorg. No? It basically would say, okay, there's a challenge, and this challenge was uncontested, and so we're going to rewind the story of the L2 to the point where basically that data was not available. No? And so this requires a smart contract, and this requires a very subtle but important thing. When you create this kind of challenge contract, you need to be able to say, hey, I ask for this key, for this DA commitment, and you show me the data. No? And how do I know that the data you show actually belongs to that commitment? To actually do that, you need to be able to, let's say, the simple version would be like the commitment should be like the hash of the block. So I could have a smart contract that basically hash the whole data and say, okay, it's the same data. Cool. So let me talk about Eigen first. No? So Eigen, the idea is a DA solution. It's an off-chain DA solution, has these kind of 3 steps. No? It's going to be something that's called encoding. Then it's going to be doing disperse and attestation. And finally, it has something that they call bridging. The idea is like, this is designed to be horizontally scalable. And so the idea is like, you're going to talk, maybe I'm going to show it here first. You're going to talk with what they call like a disperser. So a disperser is a service that they run. And then these Ethereum validators that are part of Eigen DA can run what they call like these DA nodes. And so the disperser is going to get your blob, is going to do erasure encoding into that, is going to put all of that into a KCG commitment, into a polynomial commitment, and it's going to send chunks, no, this part of this blob to the different DA nodes. And so why does this scale? Is because you can actually have as many DA nodes as you want, and that's going to give you a lot more bandwidth that you can basically use. No? So this scales with that. And so the first part that I was mentioning, like this encoding and erasure, it's the erasure encoding, and then getting all of that into a polynomial commitment, and I guess generate all the chunks and send all of those to the DA nodes. Now the DA nodes are going to get a chunk, and it's going to return a signature saying, hey, I saw that chunk, I'm holding it, I'm going to store that. That's going to be part of a BLS signature, and so the disperser then is going to get all those BLS signatures, is going to aggregate that, and that's part of what they're going to give to you, I guess the client. I'll say, hey, here's a BLS signature, here's the proof that your blob has been stored on Eigen. Now, if you are like talking to a disperser and using HTTP or it's HTTP, that's okay for you. You will have that data. But what if you are a rollup, or what if you are a smart contract and you want to kind of know that actually that happened? So they do another thing for that. That's what they call bridging. No? So when you go and call the disperser is going to get your blob, it's going to store it using this process that I explained. And the second thing it's going to do is going to add that into a batch. No? It's going to basically have as many blobs. It's going to have, like, I don't know, let's say, I think it's for 10 minutes more or less. It's going to accumulate all those blobs. It's going to put all of them into a Merkle tree. And it's going to call all of that a batch. And it's going to send that batch, or the batch header with like the batch root to Ethereum. And thanks to that, you can basically go and prove that your blob has been attested. It's basically part of a batch, no, on Ethereum. And by doing that, you can basically use that knowledge from smart contracts on Ethereum. Okay, that's again not necessarily what you will use, but it's actually what it's going to give you certainty that it has been attested, has been stored, and is going to be available. Okay, final thing that I guess I wanted to go and talk is how you mix all those things together. Now I talk about OP LDA, I talk about EigenDA, how all these things work. So this is basically what I describe about OP LDA or Plasma, and this is what I'll be describing about Eigen. Now, the way it works is like, again, you still have the sequencer. The sequence is going to talk with this Plasma server. There's actually one that exists. It's called Eigen proxy that implements that standard. The Eigen proxy is going to be talking to the disperser, which is part of EigenDA, and EigenDA is going to be doing the DA nodes, going to be talking to the DA nodes. The same thing as a full node, you will be able to go reach the Eigen proxy and going to get a blob, no? And you're going to get all the data. Now, for DA commitment, it's not going to be the hash, as I explained as a simple case. It's going to be more of like a serialized data structure that contains like the blob, the batch, where this was stored, the batch header, and some Merkle proof to kind of show you that you can actually verify that actually exists. And again, if at some point it failed, you could always go and do the challenge, no, and say, okay, show me the data, right? Show me the data that you said you had, but you are not willing to give to me, and you can create a challenge. Again, for that, you will need a specific kind of contract that is able to understand like the DA commitments of Eigen, which is, I guess, in construction right now. Now, I said this seems very simple, but it's actually not that simple right now. When you actually, the disperser, I guess, as I said, puts everything into a batch, and it's also going to consider that your blob it's like fully like confirmed only when that batch has gone to Ethereum. That actually takes some time, and so the way they work, it's basically you post a blob, they give you a request ID, and then you can actually go and query the disperser as many times as you want to see if like your request is done or what's the state of your request. No, and so you can imagine that first phase is going to be error encoding and then send that to the DA nodes. That's probably good enough for some use cases. Then it's going to tell you, okay, I already include that into a batch, and the batch is closed. No, and finally, it's going to send that batch to Ethereum, and it's going to tell you, okay, it's done on Ethereum. Here's the transaction, or even more, it's on a transaction on a block on Ethereum that it's already finalized. No, so that actually takes some time. So a few things that I wanted to mention here that I guess are kind of missing pieces that we are working on, either by ourselves or with EigenDA or with OP. So as I said, the challenge mechanism, the OP Plasma initial version relies on the idea that DA commitments are hashed of blobs. Here is quite different, and so there's a need to actually create this kind of challenge mechanism for this to work. The second is like, as I said, the disperser takes actually some time to do the writes, several minutes, and so we are working actually in like making many or concurrent writes because you don't need to actually wait for that, and they're also working on like actually having all of that in a faster fashion. Another thing that I didn't explain too much, but if you see this diagram, you see that from a system perspective, like the disperser seems to be like the central point of failure, right? Like they run the disperser, and the disperser is down, well, everything is down. Again, it's a server, it's a service that you can, I don't know, have all your like technology and ops to make it fault tolerance, replicas, and everything. but it's still going to probably be run by a single organization. And so the idea, they're also part of Eigen, is to go and decentralize this, and so you could potentially run your own disperser. This is not something you can do now, but would be important for the future if you want this to really, really work. And finally, this is more of our own addition, which is called like a backup service. And I'm probably going to be discussing now with when I talk about like failure scenarios. So when we, I guess, as I mentioned at the beginning, we are working on integrating OP with EigenDA and run celo on top of that. And so one of the things we started doing was try to understand how this could fail, what would be our response, what would be the response of our system in those scenarios. No? So I guess you have like two typical like buckets. No? You can talk about write failures. So imagine you are the sequencer, you create your own transaction batch, you want to talk to this service, you want to write that, and let's say the disperser is down, and so you are not able to communicate with that. Or the disperser responds, but what doesn't respond doesn't really verify. No? So they give you a DA commitment, but the DA commitment doesn't match what you expected. Those are, for us, maybe the similar thing for us. It's the same thing, like write fail. And there's two types of solutions you can have, or I guess three. So, you know, like chains have like, I guess, two options, right? When it comes to failure, they could say to prefer liveness, and so they say, okay, I'm going to continue working even if I can guarantee this is going to be final, and I'm okay with reorging. No? So that's, for example, like how Ethereum tends to do. They prefer liveness over safety, or you can prefer safety and say, okay, I'm not able to progress because the conditions are not met, and so I'm going to stop. No? And depends on what kind of system you want to build, you can say, okay, what's with my preference? So in this scenario, okay, you can write. So you can stall. You can say, okay, I'm going to stop. You can choose liveness too. You can say, I'm okay with reorging when this happens with this change. Or you could also have like a secondary server or mechanism to write. For example, you can go and talk to send the data directly to Ethereum as cold data or as blobs. Or you could have a secondary DA service for these kind of things. Now, that's okay. This actually is more challenging. So what happens if a read fails? What happens if the disperser goes down or the disperser sends something that doesn't verify? So the first thing is like, well, you know that you have the challenge mechanism. So with the challenge mechanism, if read failures, it's going to generate a reorg. No? So that's actually solved there. But maybe that's not what you want. I guess in our case, we prefer to have safety over liveness. So we want to have like what we call one block finality or reorg resistance. And so we don't want to reorg at any cost. So in our case, what we are thinking is actually have like a bit of a backup service. Whenever you write, I guess we will probably write that ourselves, at least as a training wheel for this system, so you know that you still be able to read whenever you want. And I guess I'm on time, and this is all that I wanted to show. Yeah.
Thank you so much, Mariano. We have time for just one question. If anyone's got a question, please feel free to give it now. Yes.
So I'm curious to why you chose to use a data availability service. Now that on L1 we are in a blob world, and rollups use 4844 blobs, which are quite cheap, and there's a separate fee market from the call data. Is there still benefit to like using a data availability service over blobs, or is it just cost?
Yeah, so I think it's probably a cost, and the problem we see, how we see is like, I think right now with product sharding, the costs are pretty low, and it's not being the bottleneck anymore. At the same time, we are seeing all these L2s posting and starting to be coming on Ethereum, and so it's very hard to gamble or know is like, okay, are the costs going to, is like the supply of blob space is going to be as it is now, or because the demand is going to grow so much, the costs are going to increase again? So when you are trying to make this kind of long-term decision, you are saying, okay, always a bit of a gamble. You say, okay, well, maybe the demand is going to increase, but then it's going to arrive dunk sharding, full dunk sharding, and we're going to be okay again. But still like a bit of a bet, no? So I guess this would be more of like a conservative approach where we say, okay, we know that we can have actually much cheaper DA in a way that it's going to always work without taking that gamble. The whole thing is like, again, on these systems, you could eventually change if you wanted. The nice thing about that, I haven't really described that from this RDA or plasma solution is like, whenever you say a DA commitment, you basically, you send like a DA commitment of type X, no? And so you could basically, when you are reading those DA commitments, no? Imagine it's basically a full node reading from a queue and reading messages. And so you say, okay, this is a blob DA commitment. I'm going to read it this way. This is an Eigen DA commit. I'm going to read it this way. And you can do all of that. And so eventually you could basically have a multi-DA system or with fallbacks, as I said, or you could switch. So I think that's interesting too from a system perspective.
Awesome. Thank you very much. Another round of applause. Right,